In this video, we're going to work a few selected problems to help practice for the Chapter 7 test. So first, we're going to take this derivative. So we have x times the arctangent, so we're going to do a product rule. So there's the first times the derivative of the second, which is, remember, the derivative of an arctangent is du over 1 plus u squared. So du is the 2, and then we're going to get 1 plus the quantity 2x squared, plus the second, which is arctangent of 2x times the derivative of x, which is 1. Then we move on to the second one. So we have a constant 1 minus 1/4 times, now the derivative of a natural log u is going to be, remember, du over u. So du is going to be the derivative of 1 plus 4x squared, which is 8x. And then the u is going to be that 1 plus 4x squared. So we can see that we're going to get some cancellation here. And we can multiply numerator and denominator here. So that's going to be 2x over 1 plus 4x squared plus the arctangent of 2x. And then that's going to be a minus 2x over 1 plus 4x squared. And we step back and see that these are going to cancel each other out. And so our answer is just the arctangent of 2x. Okay, the next one, this is the arc cosine of square root of 1 minus x squared. Remember, our derivative for an arc cosine is a negative du over the square root of 1 minus u squared. Now the du is going to be the square root of 1 minus x squared to the 1/2, which is a chain rule derivative. So the du part is going to be a negative 1/2, and then we're going to have 1 minus x squared to the negative 1/2 times the derivative of the inside function, which is a negative 2x. And that's going to be over the square root of 1 minus, and our u is that square root of 1 minus x squared squared. Now, calculus is done, algebra begins. The negatives will cancel, the 2's will cancel, and we're going to move this down below as a radical, so only that x remains in the numerator. We're going to get our square root of 1 minus x squared that just came from the numerator in the denominator. This square and that radical will cancel, so we're going to get a 1 minus the quantity 1 minus x squared that is still in that radical. So when we distribute, we'll get a 1 minus 1 plus x squared in that radical, and the 1's will cancel, and we'll get the square root of x squared, which we want to remember is actually going to be the absolute value of x. So our final answer, now this x and that absolute value of x cannot cancel because they are not always equal to each other. And so our final answer is going to be x over the absolute value of x times the square root of 1 minus x squared. Okay, now this is a challenging one. Our first try, we want to say, well, if u is x squared minus 4x plus 5, then du would be a 2x minus 4 dx. And so we look there and we say, oh man, if that was only a 2x minus 4, we would have a perfect match for our du. So we're going to make it a perfect match. We're going to, we need another minus 3 there, so we're going to subtract 3 and add 3. So now what we're going to get is the 2x minus 4, that would be a perfect match for our u substitution. And then we're going to get this other integral, so we're going to get a plus, I'm going to move it over here, a plus the integral of 3 over x squared minus 2x plus 5. Now, the one in the green, we're well on our way. We've got exactly the substitution we want. So the dx is going to be du over 2x minus 4. And this integral will become, here's our 2x minus 4 that we kind of helped create. We're going to call all of this stuff u, and we're going to replace the dx by du over 2x minus 4, which is great because those are going to cancel. And we just get the integral of 1 over u du, which we know is going to be the natural log of the absolute value of u, which is going to be the natural log of the absolute value of x squared minus 4x plus 5. Okay, now we're about half finished. So now we're going to come over here. Now the u substitution that we used here is not going to work here because we don't have that x. So instead, we're going to have to try to make this into an inverse trig function. Because we don't have a radical, we're thinking this is going to have to be an arctangent. That means we're going to have to complete the square in that denominator. So we're going to make that an x squared minus 2x. I'm going to push that plus 5 over because it's not what we wanted. I'm going to take half the middle term and square it. That's going to be 1. And then turn right back around and subtract 1. So I've really just added 0 into the denominator. So that's going to now become, we have 3 in the numerator. This part is going to now be a perfect square, which I'm going to write as x minus 1 squared. And the minus 1 plus 5 is going to be a plus 4. Now we can sort of see an arctangent emerging. We need to make that be a 1. So I'm going to bring this 3 out and the 4 from the denominator. And so now we have 1 over, and this is going to now be x minus 1 squared over 4, and we've created the plus 1 that we wanted to. We're going to look at that as u squared, so in this integral, our u is going to be x minus 1 over 2. We're thinking of that as like a 1/2 x minus 1/2, so when we differentiate that, we're only going to get the coefficient of x, and so dx is going to be 2 du. Okay, starting to come together. So now we've got 3/4. Our integral, the dx, we're going to replace by 2 du, and that denominator is now a u squared plus 1. That's going to come outside and cancel with our 3/4, and so that's going to be 3/2 integral of 1 over u squared plus 1, which was going to be a 3/2 arctangent of u, which is going to become a 3/2 arctangent of, I guess we called that x minus 1 all over 2. So I'm going to bring it over together, and we're going to get a plus, I believe it was, 3/2 arctangent of x minus 1 over 2 plus c. Whew, there's a lot going on in that problem. Oops, I guess I didn't really need this part of it. So that's going to be our answer to our integral. All right, let's look at this next one. Now, if we try making u this denominator, the 7 plus 6x squared minus x to the 4th, then du is going to be like a 12x minus 4x cubed. We don't see any x cubes anywhere around there. So that means somehow or another we're going to have to make this into an inverse trig function. We have a radical, so I'm thinking maybe arcsine, maybe arcsecant. Since we have a minus x to the 4th, we're going to try to make that into an arcsine. But notice this is next to the 4th. So we're going to complete the square in the radical there. Let's see what this looks like. I sure hope we can account for that extra x up there. We're going to factor the negative out, so that's going to be x to the 4th. That will become a minus 6x squared. I'm going to move that plus 7 to the outside, and now we're going to try to complete the square. Half of 6 is 3, 3 squared is 9. We're going to add 9 in, but that's getting multiplied by that negative, so I'm going to make it be 0 by adding another 9 in. Let's see where this leads us. Now we're going to have the 16 is going to come in front of the minus sign. That x to the fourth minus 6x squared plus 9 is going to factor into x squared minus 3 squared. Aha. Now we're going to pull out that 16. It'll come outside the radical as 4 and outside the integral as 1/4. I don't know if you see where we're going yet. This is now going to be the square root of 1 minus, that's going to be an x squared minus 3 squared over 16. This is going to be our u squared, which means u is going to be x squared minus 3 over 4. And in your head anyway, you can see that as a 1/4 x squared minus 3/4, which means that du, we're going to get a 2 times 1/4 is 1/2 x dx. Notice our du is going to pick up this extra x. So the dx is going to be 2 over x du. All right, we're making progress. We've got this 1/4 integral. That x we're going to count for here shortly. We've now got the square root of 1 minus u squared, and our dx is going to be replaced by 2 over x du. We can cancel those x's. That 2 will cancel with the 1/4, so it's going to be 1/2 integral of 1 over the square root of 1 minus u squared du, and that is going to be an arc sine. Wow, kind of a disguised arc sine. So that's going to be a 1/2 arc sine of our u, which we said was x squared minus 3 all over 4. Let me make a little bit better x squared there. And then our plus c. Okay. Let's look at the next one. Now we have a definite integral. So we can see here that if we just let u be the natural log of x, then du is going to be 1 over x dx, and that means dx is going to be x du. So our integral is going to become u to the third, and our dx is going to account for that extra x in the denominator. Let's just practice and call this u of 1 and u of e. And so this will become, since this is our u of 1 is going to be the natural log of 1, which is 0. And u of e is going to be the natural log of e, which is 1. So this becomes u to the third du from 0 to 1. So that is just going to be 1/4 u to the fourth, going from 0 to 1, is going to be 1/4 times 1 minus 0. So that whole thing is actually 1/4. Okay, next one is another tricky one. Now you can try to figure out for a while, what are you going to call u here? And it just doesn't work real great. Now, if you recognize that x is the square root of x squared, then since x is the square root of x squared, what we can try now is to see this maybe as a 1 plus u squared, and let's see where this leads us. If we say u is square root of x, which of course, for derivative purposes, we can think of as x to the 1/2, du is going to be 1/2 x to the negative 1/2. That's 1 over 2 square root of x times dx. That means that dx will be 2 square root of x times du. So let's see. We've got 2 from that numerator. The dx we're going to replace by 2 square root of x. And we've got a 3 square root of x, and we're going to call in the parentheses here, that we're going to think of as 1 plus u squared. You following all this? So those square root of x's will be accounted for. And we got some constants to pull out. So we're going to get a 4 over 3 to come out of that. But the integral then becomes just 1 over 1 plus u squared du, which is our arctangent. Crazily enough, that gets us to 4/3 arctangent of u, which is going to be then 4/3 arctangent of, we said u was the square root of x plus c. It was pretty disguised. Okay, we've seen this integral or ones like it before. These are always really tough. It's actually going to be a straight u substitution, but it's going to be a long and winding journey. We're going to let u be the entire denominator. So that's going to be 2 plus the square root of 5x. So we can think of that as 2 plus, I'm going to write that as 5x to the 1/2. So du is going to be a chain rule derivative. That's going to be 1/2 times 5x to the negative 1/2 times the derivative of the inside function. So that we can write as 5 rather over, let me get my pen up, 5 over, that's going to be 2 square root of 5x. There's our dx. So that means dx is going to be 2 square root of 5x all over 5 du. Looking pretty messy so far. So we've got 3 so far, and the dx is, I bumped that with my left hand, that's going to be 3 over, I got to bring my pen back up now, 3 over, that's going to be u. The dx we're going to replace by 2 square root of 5x all over 5 du. So, not quite what we want yet. Let's take all those constants. The 3 times 2 is 6, and the over 5 all outside the integral. But we've still got a square root of 5x, which we don't want, over u du. So this is where we come back to our original u substitution, and we can say, solving for the square root of 5x, that it is going to be u minus 2. So that is going to make this now be 6/5 integral. This is going to become a u minus 2 over u du. Still a tricky integral. And here the secret or the trick is to split that up and call it u over u minus 2 over u. So that's going to become 6/5 times, and I'm going to make those separate integrals. So we have the integral of 1 du minus 2 times the integral of 1 over u du. You see what I'm doing there? So the 6/5 is going to hit everything. The integral of 1 with respect to u is u. That's going to be a minus 2, and that'll become a natural log of u. And then we're going to go back to our x's. So that's going to be 6/5 times the u, which was our 2 plus the square root of 5x. And then distributing that's going to make that a minus 12/5 times the natural log. And you can put it in absolute values, but this is one where you'd still be correct if you didn't, because a radical is never going to be negative, so a positive number 2 plus a radical will never be negative either. So either one of those would be okay. Whew, that's a tough one. Now the next one, we see that the degree of the numerator is greater than or equal to the degree of the denominator, so that means we're going to have to divide. So we say what times x is x squared, that's going to be x. X times x minus 2 is x squared minus 2x, and we subtract that quantity. The x squareds drop out, 0 minus a negative 2x is 2x. And we reload. What times x is 2x? That's going to be 2. That'll give us 2x minus 4, and we're going to subtract that quantity. The 2x's drop out, 0 minus negative 4 is positive 4, so we take our remainder over what we divided by. So our original integral has now become the integral of x plus 2 plus 4 over x minus 2. Now this we can integrate. So the integral of x is going to be 1/2 x squared. The integral of 2 is just 2x. The integral of 4 over x minus 2 is 4 times the integral of 1 over x minus 2. You can maybe in your head, if possible, but you can write it out if you need to, see that this is going to be the integral of 1 over u to u. So we're going to get a plus 4 times the natural log of the absolute value of x minus 2 plus c. Here we go. All right, what we got here? Looks like we have a table of values. We're told that selected values of f are given, and f is decreasing and concave down over the whole interval. This may be important down the road. So first we want an integral expression for the average value of f over the interval from 1 to 7. So average value of a function is 1 over b minus a times the integral from a to b of f of x. So in this case, our integral expression, since the a is 1 and the b is 7, is going to be 1 over 7 minus 1 is 6, integral from 1 to 7 of f of x dx. And that's all we were asked to do, is come up with an integral expression. Now, part B is trying to get you to see the difference between the average value of a function and the average rate of change. So these are easy to confuse because they both have the word average in them. But an average rate of change, remember, that's way back to our AP prep days of f of b minus f of a over b minus a. That's really just our slope formula. Now, if we want the average rate of change to estimate, let me change that question. Let's find the average rate of change, and I'm going to say from, I don't like the way I worded that question, so let's find the average rate of change. I'll say of f, and I'm going to give you an interval here. So I'm going to say over the interval, and let's just say from 2 to 4. So we could have approximated the instantaneous rate of change at 3 by using an average rate of change. That's kind of a different question, but one that's related to it. So what we can do here is just do, I'm going to switch to white again. So we're going to do f of 4 minus f of 2 all over 4 minus 2. That's our average rate of change. And this could be used to approximate the instantaneous rate of change at 3, since we don't know the instantaneous rate of change at 3. So let's see, f of 4 is 2, and f of 2 is 8, and 4 minus 2, so that's going to be a negative 6 over 2, which is a negative 3. So there's our answer to the average rate of change. Now we're going to approximate that integral using a trapezoidal rule with 3 trapezoids. So we can see there's going to be one trapezoid, a second one, and a third one. Now these are not uniform width trapezoids, so we cannot use our formula, that 1 over b minus a times f of a plus 2 plus the f of b. So we're going to have to do individual trapezoids here. So that means we're going to take 1/2 times the sum of the bases. That's going to be 10 plus 8 are going to be the 2 bases for the first trapezoid, times the delta x, which is going to be the height, which is going to be 2 minus 1. Then the second trapezoid is going to be 1/2. The sum of the 2 bases are going to be 8 plus 2, and the delta x here is going to be 4 minus 2. And then the third trapezoid is going to be 1/2 the sum of the bases times the delta x, which is 7 minus 4. So we're going to get 1/2 times 18 times 1, and then plus 1/2 times 10 times 2, and then 1/2 times negative 6 times 3. So half of 18 is 9, and half of the 2 is 1, plus times 10 is 10, and the half of negative 6 is negative 3, times 3 is a negative 9, so our approximation is going to be 10. Now, is our approximation in part C an over or underestimate? So here's where why the reason we said in the beginning that this was concave down. So if you can imagine, this thing is concave down, and we're going to be approximating that area under the curve using trapezoids. I think you can see that we are going to be missing little spaces as we do that trapezoid. So our answer is going to be that this is an underestimate, and the reason is because F is concave down. So it has nothing to do with increasing or decreasing. That applies to rectangles, but a trapezoidal rule will be an overestimate or an underestimate depending on its concavity. All right, very good.